Hello, everyone. I'm Jaeha Kim with Seoul National University and Scientific Analog. And today I'll present a UVM test bench for exploring design margins of analog mixed signal system using a PCI-Express receiver detection circuit as an example. First, I need to explain what a receiver detection circuit is. In a high-speed interface, such as a PCI-Express, where you have a pair of transmitter and receiver. In this particular case, we have a differential pull-down current mode driver connected to a voltage mode receiver through a AC coupled channel. And to avoid reflection, both on the transmitter side and receive side, we have these set of termination registers. In order to avoid any data loss or the waste of power, the PCI-Express transmitter needs to know whether the receiver is connected on the other side of the channel before initiating the data transmission. And the spec says this receiver detection circuit must function correctly for a range of condition parameters. For example, the coupling capacitance on this AC coupled channel may vary from 76 to 265 nanofarad, and the equivalent capacitance of the channel can be up to 3 nanofarad, and both the transmit side termination resistance as well as the receive side termination resistance can vary between 40 and 60 ohm. There are many ways to implement this receive detection circuit. The one idea that we're going to consider in this talk is the one described by this patent by Guo and Yang. The idea basically transformed the transmitter into a relaxation oscillator and measured its oscillation period to determine whether the receiver is present or not. The receiver detection circuit may use its dedicated pull-down circuit, or it may actually recycle the pull-down current driver which is already part of the main driver. But it will switch that pull-down current on and off depending on whether the output voltage, the transmitter output voltage, is higher than the VREF-H, the high side voltage, high side reference voltage, or lower than the VREF-L. Let me walk you through the operation process. Initially, when the pull-down current is off, then we have the output node connected to VDD through this termination resistance. And there's an additional capacitance where we have the CC, the coupling capacitance, in series with the channel capacitance. So it will increase, the output voltage will increase towards VDD with the RC time constant set by these resistance and capacitances. But when the output voltage reaches high enough, reaching the high side reference voltage, VREF-H, we have this control, the feedback circuit turning on the pull-down current. And from then on, due to the voltage drop across this resistance, now the output voltage will start decreasing. Now, when that decreasing voltage reaches the low side reference voltage, VREF-L, then we turn the pull-down current off again. Then the output voltage starts rising again. Okay? So by switching on and off the current, the output voltage rises or falls, and we'll repeat that process. And basically, this is an oscillation circuit. And turns out the presence of the receiver will change the oscillation period of this circuit. The case that I just explained is when we do not have the receiver present. In that case, the output voltage, we call it, it's the transmitter common mode output voltage, the VCM. It rises and falls with a time constant set by the resistance R, the termination resistance R, times the series combination of CC and CCH. Most of the time, CC is much greater than CCH, So the series combination is limited by the smaller one, CH. So the resulting time constant is just R times CCH, which is quite short. In other words, the circuit will oscillate with relatively short period. On the other hand, when the receiver is present on the other side of the channel, we have this additional receive side termination resistance connecting across the channel capacitance CCH. So that effectively shorts out the small CCH, leaving only the large CC. As a result, the time constant for the output common mode voltage rising and falling increases to the sum of the two termination resistances times the large CC. In other words, the circuit will have a long oscillation period when the receiver is present. So in conclusion, we can detect the presence of receiver based on the oscillation period, whether it's long or short. So here's another way. Well, here's the way of implementing this circuit into some mixed signal feedback loop. The mixed signal feedback loop has four components: the common mode voltage sensor, three-level quantizer, digital controller, and a pull-down current driver. First, the common mode voltage sensor, the VCS sensor, measures the common mode of the two transmitter output voltages. And the three-level quantizer will compare that voltage against the two reference, Vref8 and Vref-L, to produce a quantized, quantized output of that signal into a 2-bit, the 2-bit quantized output. Now, the digital controller will either turn on or turn off the pull-down current depending on the value of that 2-bit quantized output. And the pull-down driver will either turn on and turn off based on that control input from the digital controller. Now, this digital controller in the middle will also measure the oscillation period, the period of the pull-down current being on, and also the period of the pull-down current being off. So it is the digital controller that can make a decision whether the receiver is present or not, depending on whether this digital count of the oscillation period, NP, is greater than or less than the threshold, NP thresh. So it can produce the RC detect signal indicating the presence of the receiver. So remember that this receiver detection circuit must operate correctly for a range of condition parameter values, like the CC, CCH, R term 3X, R term RX can all vary, with certain range. That means the NP value reported by this receiver detection circuit, either with the receiver present or not present, can change, can vary over a certain range. For example, NP value with the receiver present will be a large number. We expected them to be a large number. It can vary over a certain range. And similarly, the NP value without the RX present can also vary. And what we expect or what we need is that the minimum value of NP when the receiver is present is greater than the maximum value of NP without the receiver being present, so that we can use the value in the middle as a threshold, and we compare the actual measured NP against this threshold to determine the presence or absence of the receiver. In other words, if we have a good separation, large separation between these minimum NP and maximum NP value, we have a large design margin in the circuit, and the circuit can reliably detect the presence of the receiver. So the goal of this work is to build a UVM test bench that can characterize this design margin of a PCI-Express receiver detection circuit. Namely, we like to have this test bench measuring the minimum NP value with the RX presence across the whole range of the condition parameter that I described. Also, when the receiver is not present, We want to measure the maximum NP value across these range of condition parameters. So the one thing I'd like to emphasize is that these condition parameter takes a continuous value. They span across a continuous range. So it is not possible to try every single value within the range because it's not a finite number. So to achieve this goal, we need to address two challenges. First, we need to model this PCI receiver detection circuit, including some analog components, in system Verilog, since only then we can use the UVM Testbench. And also, we need to build a test bench that can find the minimum or maximum values of NP while exploring a continuous value parameter space, as I said. Among them, the first challenge can be addressed by using X model, which is a product developed by Scientific Analog. So to give you a brief introduction, X model is a plugin extension that works with the existing system Verilog simulator like VCX, Excellium, and Questa, enabling very fast and accurate analog mixed signal simulation. It has a very powerful event-driven algorithm that deliver a much faster speed compared to the real number model describing the equivalent circuit. And when it comes to modeling analog circuits, it can model both a functional model. It can support both the functional model and the circuit level model. I'll describe more detail about this shortly. Nonetheless, all the models supported by X model is fully compliant in system Verilog. That means that model can run within the system Verilog without any Spice-like engine involved. And that means we can use a UVM test bench on top of it. Everything kept with it inside the system Verilog, 100%. The reason X model is so fast is because it performs an event-driven simulation of analog circuits while running all the simulation, performing all the steps within system Verilog. And the set of waveform on this slide kind of illustrate the event-driven algorithm of the X model. The first waveform is like the output of the transmitter transmitting some digital data like ones and zeros. And the green waveform in the middle is the signal after this, the blue signal propagate through a lossy channel. And the red one is the one after the equalizing filter. What you notice is that the number of markers, which indicate the events being triggered during the simulation, are very few, and they're very sparsely distributed. In fact, they're being triggered only when there is an event at the corresponding input. Okay. Still, we can describe the change in the waveform between these two events very accurately using an equation. So in other words, each event in X model is not just computing the value at one particular time, it is actually updating the equation that describes how the waveform varies over time. And by updating this equation, only when there is a corresponding change in the input equation, we keep the simulation very fast without losing the accuracy. Okay. And another advantage of X model is that modeling analog circuit within the system Verilog is very easy. You can just put together the X model primitives as a building block. And you can compose both the signal flow model on the left, using the functional primitives of the X model, or you can also build a conservative system model, in other words, a circuit level model, by putting together what we call circuit primitives of the X model, such as resistor, voltage control voltage source, and a capacitor primitive, each modeling the corresponding elements in analog circuits. Let me tell you more about this circuit level modeling. So using these circuit primitives of X model, you can model analog circuit simply by listing their elements directly in system Verilog. This is almost like just writing netlist. It's a spite netlist, just that it's in the system Verilog syntax. And compared to using some real number model features, such as the user-defined resolution function, or maybe EENet, which is kind of an indirect way of describing these analog circuit behavior. This way of using the circuit primitive is the most natural way of modeling various analog circuit effects, such as the nonlinear effects, switching effects, as well as the loading effects. In our PCIe receiver detection circuit, we have the current switching on and off, so that includes the switching effect. And also, depending on whether you have the receiver present or not, whether we have the receiver side termination, present or not, we have a different time constant for the rising and falling transition. That's essentially a loading effect. And we can model all those effects very easily in a natural way using these circuit primitives. So let me describe that using the actual, by describing the actual model we use for the RX detection circuit. Let's start with a common mode voltage sensor, the VCM sensor. This block measures the common mode of the two transmitted outputs with a pair of resistors. And these resistors are connected to the output only when it's enabled. In other words, what we need is a pair of switches. And for that, we can use the switch primitive of X model, which essentially models a variable resistor whose resistance changes depending on the digital control signal enabled. Okay, so that's easy. And once we have the measurement on the common mode voltage, we have this three-level quantizer that compares that VCM against the two reference voltage, VFL and VFLH, and generates a 2-bit quantized code ranging from 00 up to 11. Well, it's actually a thermometer code, 00, 01, and 11. And again, it can be simply described by listing these X model primitive. In this case, we use a compare primitive with each modeling a clock comparator, which samples the input and makes a comparison between the input and the reference and produce a digital data depending on that difference polarity. Now, the digital controller in the middle, it will switch the current on and off depending on the quantized output, and it will also count the oscillation period at the same time. And since this is a digital controller, this can be described in pure Verilog, as you see on this slide, where the first always block, performs the control, like it will, generate the control signal for switching the current on and off, depending on the quantized output. And the second always block will measure the oscillation period NP using a simple counter. So this, X model is based on system Verilog, so it can describe parts of its model in pure Verilog easily. Now, finally, the pull-down current driver, which pulls the common mode current from the TX output, depending on the control input, can be described as a pair of I source primitive, which generates the actual current pulled from that output voltage node. And the AND X bit is a logic gate primitive of X model that performs the AND gate to enable this current only when it is enabled, when this enabled signal is high. And the transition primitive that will produce a desired output current level by translating the digital input to an analog value. Okay? So this, what the set of these slides demonstrates that just by putting together these X model primitive, you can model a fairly sophisticated analog circuit, such as this RC detection circuit. Now that we have taken care of the problem of modeling these RC detection circuit in system Verilog, next is to build a UVM test bench that can explore the design margin of that circuit. The UVM test bench that we're going to present has three major parts: the driver agent, the fixture, and the scoreboard. The driver agent searches for the condition parameter value, namely the coupling capacitance CC, the channel capacitance CCH, and the termination resistances R term TX and R term RX that tries to either minimize or maximize NP, depending on whether the RX is present or not. Now, once the driver agent generate a new set of parameter value to try, the fixer will actually apply those values to the test bench and run the receiver detection circuit and measure the resulting NP, the oscillation period count. And we'll send it back to the driver agent so that the driver agent will consider that outcome and pick the next value that is most likely to reveal the minimum or maximum value NP in the next trial. Now, in the meantime, when the driver agent and the fixture, gives these, information back and forth, the scoreboard listens to all those transactions and collects the minimum NP with the receiver present and the maximum NP without the receiver present. And it is a scoreboard that will report the end result when the simulation all finishes. Let me give you more detail about each of these components, starting with the driver agent. The driver agent finds the optimal set of these condition parameter, CT, CCH, R term TX, R term RX, that either minimizes or maximizes the NP. Okay? To do that, it uses the reactive stimulus technique. In other words, it tries a few points, and based on the outcome, it will pick the next trial, in an adaptive fashion. And in order to choose the next set of points to try, based on the previous outcome, it uses the Bayesian optimization algorithm. The Bayesian optimization algorithm basically constructs a surrogate model based on the previous trial outcome, and it builds a model and uses the model to predict the outcome of the unexplored point. And once you have enough number of trial, you have a reliable prediction across the whole continuous range. In the end, you can find a point that will give you either the minimum or the maximum NP. So to do that, we have built a 4 DPI function wrapping around some open source package called BaseOp, implementing these Bayesian optimization, namely BaseOp initialize, select next, update model, and get optimum. So just walking you through these code. First, we execute BaseOp initialize DPI function to initialize the surrogate model across the range that for the range of the condition parameters. Now, for a sum number iteration, we actually try 200 iteration for each of the case with the receiver present and not present. Then we use the BaseOp select next to choose the next point to try, and then feed those value to the fixture by assigning those values to the packet and sending that packet to the fixture through the driver component. And then we wait for the response from the fixture, and based on that response, we update the model of the surrogate model. Update the surrogate model. Now, using this updated model, we can make more refined the selection on the next trial point. And after the 200 iteration, then we can now choose the optimum condition parameter that is most likely to result in either the minimum NP or the maximum NP. The next component in the test bench is the fixture module. The first part of the fixture module uses a handshaking protocol to receive the condition parameter value and then try that on the receiver detection circuit and send the response back to the driver agent. And we would like to do that multiple times during the single simulation run. And that's why we're using this handshaking protocol. The handshaking protocol actually essentially uses two signals to indicate the start and completion of the each trial, start and done. So again, walking through this code, first we wait for the start signal to go high, and that's done by the driver agent. Once it is done, the fixture will retrieve the new set of CC, CCH, R term TX, and R term RX, and apply that to the test bench configuration. Now, it will enable the RX detection circuit with that new condition and let it run for some time and wait for that receive detection circuit to produce the output response. And one of the output response it will contain is the NP value. So it will collect the NP value and send that back to the driver agent. And it will assert a done signal. And when this is done, the driver agent will retrieve that NP value using the Bayesian optimization algorithm. Will pick the next condition parameter value to try. The other part of the fixture module includes the test bench configuration. This is the part that will contain the RX detection circuit itself, our device under test, and we will need a transmitter with the AC couple channel, and we will need to connect or disconnect the receiver depending on the condition we like to apply. And some of these circuits require a clock input as well as the supply voltage input. So we have the primitive that can feed those signals in. Okay. And one thing I'd like to point out is that for the capacitance and the resistance modeling our condition parameters, namely the CC, CCH, R term TX, and R term RX, we use a special X model primitives called cap SW, res SW, which model the capacitance and resistance, whose capacitance and resistance value can change as a signal input. So instead of using a normal capacitor primitive and resistance primitive, whose R and C value are fixed by the parameter, we can now have these R's and C that can change over time, which is what we need to build this test bench. All right, last one is the scoreboard component. So this scoreboard component listens to all the NP results broadcast by the driver agent, and it will keep track of the minimum NP among them, as well as the maximum NP among them. Okay, and when the simulation is finished, it will report the those numbers using these output, like the minimum NP with the RX present, in this case, it's 2507, and the maximum NP with the RX absent, 223. And what we expect is that the first number is larger than the second one, which is true in this case. So this is the, this indicates that the RX detection circuit is working properly, and we can use the number in the middle as the threshold to determine the presence of the receiver. But the question is this receiver circuit, can this receiver circuit reliably operate across the range of other condition parameters? For example, VREF-H and VREF-L. The previous result that I mentioned assumed that VREF-H is precisely set at 1.75 and VREF-L is set at 1.35. And again, in that case, we have the minimum NP with the RX of 2507, which is much greater than the maximum NP without the receiver present, which is 223. And then let me point out that to get each of these simulation results for a one set of VREF-H and VREF-L values, we let the UVM Testbench run to perform 400 iteration, which took only 90 seconds total. Okay, and then repeat that simulation while varying the VREF-H from 1.7 to 1.775 in 25 millivolt step. And also we vary VREF L from 1.4, from 1.3 to 1.4 in the same 25 millivolt step. And what you notice is that, oh, in some cases, the circuit does work properly, producing the minimum NP larger than maximum NP. But in some other cases, the circuit may not oscillate at all, not producing the NP. And in some other cases, we have the minimum NP with RX lower than the maximum NP without RX. In this case, we have an overlap between the two ranges, and we cannot distinguish these two cases reliably. So to determine that, we computed the design margin. We calculate design margin as the difference between the minimum NP and the maximum NP divided by 2. This is the separation between the ideal threshold in the middle and the either to the other end, to the other end. So, and the larger design margin is better. And again, at the nominal point, we have a fairly large design margin of 1,142. But what you notice is that even with a slight change in the VFH or VREF-L, especially whether it decreases, VREF-L decreases, or VREF-L increases, that design margin, quickly decreases. And if further changes in that direction, the design margin becomes negative, which means the circuit stops operating correctly. Okay? So in a nominal condition, the circuit works great with a large design margin, but that design margin is highly sensitive to the change in the reference voltage values. So maybe this is not too suitable for a production circuit where there are some uncertainties in these reference voltage values. So in summary, I presented a UVM test bench that can characterize a design margin of the analog mixed signal circuit. And this particular test bench finds the worst case deviation of some circuit response, for example, the oscillation count NP, across a continuous valued parameter space. We have 4 parameters that will have a continuous range. And to build the test bench, first we use the X model primitives to model the analog components in the circuit. And we found that the circuit primitives of the X model are particularly useful in modeling this PCI-Express receiver detection circuit, which contains both the switchable current as well as the change in the condition in the R's and C that affects the time constant of the oscillation that determines the oscillation period. And to find the condition that either results the minimum or maximum the response, we built a test bench that combines the reactive stimulus technique with the Bayesian optimization algorithm. And it can essentially perform a search across the whole continuous parameter space in an efficient and adaptive way. So in conclusion, I believe this work, although it's very simple, paves the way for adaptive and coverage-driven AMS verification. Thank you for your kind attention.